All right, so, well, I suppose you know me. My name is Jonas Baltrusaitis. I'm from Lehigh University, and I'm a chemical engineer by background. And today I'm going to be talking about the solid nitrogen fertilizer recovery. So I have the titular talk, and I'm going to be slightly broad here to put a little bit into perspective, and obviously talk about the most interesting person, me, what I do in my lab. I'm also editor-in-chief of the new Sustainability Science and Technology Journal. So, go ahead and consider submissions to that journal. It's a very broad journal that encompasses many concepts of sustainability. Right. All right. So I'm mostly motivated by nitrogen cycle and agricultural sustainability. So nitrogen cycle is very, very complex. It's much more complex than, let's say, phosphorus cycle is. And if you look at these planetary boundaries, you can see that not only does it entail the chemical inputs and production, but it has the CO2 tail, it has complex nitrogen transformations into hydrogen and ammonia, and then it has all these long-lasting impacts of reactive nitrogen gases. That's why National Academy of Engineering deemed this problem of managing nitrogen cycle as one of the grand challenges of the 21st century. There is no need to say here, but I'm still going to do that we need for sort of conceptually new approaches to recover and stabilize the nitrogen. The recovery is just one part of it. Making it stable in the environment is the whole different spiel that we also need to account for. And because you can see that the nitrogen from Midwest Corn Belt region, including Nebraska, ends up somewhere in the Gulf of Mexico, and about half of it comes from mineral fertilizer inputs. That's why, if you think about it, it's quite a profitable challenge. It's a hard challenge, but it's a very profitable challenge. And some commission decided that it's worth about $2.3 trillion annually by 2030. So I say, shut up and take my money, and let's work on this problem right away. So I always start with a figure that I borrowed from Trevor 6 years ago. What is Trevor? That I took from you 6 years ago, and I always give Trevor courtesy shout to it, because I thought it was an amazing figure. It was never published for some reason, Trevor, but I thought it was amazing, even though you couldn't give me the exact inputs of the flow. But I always use the Trevor figure. I modified the things below, and I say that these reactive nitrogen flows, as Trevor says, account for large amounts, so 120 teragrams of nitrogen per year. So it trickles down, all the way from Haber-Bosch to the farms, and then it has to stay somewhere. Only very small amount of it reaches the plant, the actual plant. So there is large amount of reactive nitrogen that can be recovered in waste streams, in sort of organic urea form, ammonium form. People work a lot with nitrates, electrochemical nitrate reduction into ammonium, and similar. But sort of when we conceptualize it with whichever it was 6 years ago, I still think this is where we proceed. So after you recover, you purify. So that's one thing you want to do with these compounds is get the pure nitrogen compound. Once you get them, this is where my spiel comes in, where how we think about stabilizing and formulating them. So urea or let's say and the ammonium salts, they are not equal fertilizers. Struvite, we know how to recover it. Still, nobody wants to use it. It's very difficult, very low nitrogen content, and so on and so on. So there are things besides recovery that need to be done to make these things into, in terms of purity, of concentration, just for pure usability in agriculture. A very famous figure, if Ganga is looking at it and smiling. That's why I'm picking these things that we all have done or seen, or that's why we're all here. And some of these things, such as urea, we kind of know what to do about them. The emerging thing with what I do also is trying to stabilize urea by co-crystallizing it with something. So people from Kansas did that initiated this work around 2018. That's when I started working around this time on the same concept. And if you think about urea, just a very loosely bound, physically bound urea molecule in a crystal, and that's why its cohesive energy is so small and it's very, very unstable. So if we co-crystallize it into some syntons, it's a very fancy word for just not different co-crystal, you can potentially obtain different property materials. So in a broad sense, if you have some property on the y-axis, such as solubility, just one of the properties as an example, and on the y-axis, on the x-axis, you have, for example, triple superphosphate and urea, they're going to have wildly different solubilities. Now, when you co-crystallize these things, so if you take urea and TSP into co-crystal, the property is going to be likely in between those of the parent compound. And you can think about it that, if this is an organic compound, it's very low solubility. Urea is orders of magnitude higher solubility, so you can target, or fine tune your properties of the material to release nitrogen and to solvate with water. And indeed, if you look at it, some ammonia emission experiments as a function of time of urea versus 4 co-crystals right here of urea, so calcium sulfate, hydrogen phosphate, so TSP, magnesium sulfate, magnesium phosphate, they have very different release patterns from urea. Urea prills alone are blue, and there is some missing nitrogen balance here. Maybe it goes, denitrifies purely. And for example, a co-crystal of calcium sulfate with urea is very, very slow linear release pattern of ammonia. Now, some of these have been done before. So Fraser has several very famous papers on these co-crystals. Now, if you put your, sort of scientist hat on, and you read these papers, you can see that, the TSP was reacted with saturated urea solution, and then was slow evaporated, and then phosphoric acid, soluble calcium salt was added to precipitate out. Obviously, as a scientist, you can do that, and you can get this co-crystal in this tiny sliver on this ternary diagram of urea, P2O5, and water, and you end up with a beautiful co-crystal where the central calcium atom is bonded to the several urea molecules and then HPO4. Now, again, as a scientist, you can do that, but as an engineer, you think about it, and if you evaporate anything, a lot of energy goes just to heat up and to heat up water molecules, right? So you waste a lot of energy. So if I put my engineer hat on, I say, well, let's not do solution chemistry whatsoever. Let's do none of it. Let's disregard it as good engineers, and let's do something brute force, literally. So we call it mechano-synthesis or mechanochemistry. And the concept is emerging sort of green chemistry, where if you have a bunch of reactants and impart some mechanical energy, if the energy is high enough, if this ball impact energy is high enough, you can go through elastic, plastic, and then into chemical reaction. So you can actually go from these parent materials into this co-crystal that is a product that we're after. And it's not like a new concept in mineral industry or fertilizers. Mechanochemistry, milling has been known for a while, and even milled Morocco phosphoride has been known to release more phosphorus than just mined material. And then sort of we took off with it, and we've worked with many colleagues and crystal engineers from Italy, some of Donata and others from Lithuania, and we really went into this urea co-crystallization for agriculture. I think that was an open field at that time, right? Because this co-crystallization for pharma has been around for a while, right? That's how people patent things, right? But this co-crystallization in agriculture was just wide open field, and now I see papers coming out from Purdue, a lot of papers from China on just using this concept. So I can't keep up anymore with my group. And several interesting concepts emerged. So in 2018, we took literally very insoluble materials, so carbonates, hydroxides, and oxides of magnesium, calcium, which are nutrients also, and we can mill them mechanochemically with precursors of, with urea acids, for example, and we would get the same co-crystals So now we sort of opened up an avenue for our feedstock, which is not necessarily salt, but it can be underlying insoluble mineral. It can also be dry well waste. It's a calcium sulfate dihydrate. It's a gypsum, which is, in Europe is unheard of, but in the US, there is a tremendous amounts of it being recycled. We also made it with phosphogypsum, right? Byproduct of phosphorus production is, as long as it's not radioactive, right? You can incorporate into a co-crystal and you can return this calcium and sulfur back in the environment. Those are good nutrients. We sort of then diverged into ammonia ions. So we went into double salts. So for example, this is a very desired calcium ammonium hydrogen phosphate, and it has two polymorphs. And if you try to synthesize that from sort of by reactions of ammonium with phosphoric acid neutralizing some calcium salt, it's very, very tiny sliver where you can get it. In fact, this wasn't never reported to be obtained practically, right? If you just miss this composition, you go into some, hydroxyapatite or other components. And, it's done by neutralizing, dissolving, precipitating, washing, and getting a conversion. We didn't do any of that. We said, we don't want to do that. We just milled equivalent amounts and we obtained 100% conversion of that double salt that contains calcium. It can be magnesium and phosphorus in ammonia. Very recently with Julia and others, we made some copper, zinc, urea sulfate co-crystals. So, copper and zinc, they have their own virtues in the environment. If there's not too much copper, obviously. And you can see that, for example, the nitrate that Julia measured in soil for the co-crystals, it's much lower than urea or bare soil itself. So sort of it has some delayed action effect. And this adjusted soil respiration CO2, you can see that urea is very, very high, whereas those two sort of correspond to slow release. And then again, solubility, this ammonia emissions ratio to urea itself. So urea would be 1. They are much less than 1 for the 30 days, for example. And so see Julia's talk on that. And we've been patenting this thing. We've been working with industrial entities. So we sort of devised the patents, and these 2 patents now are mature, and we are looking to fully commercialize it. And we diverge into other technologies. Again, Julia probably is going to be talking about. But why I'm here is, I'm here to talk about real challenges in terms of recovery, and those are ammonium in my mind. So if you think about ammonium as the emerging nitrogen sink, let me see my time. Okay. If you think about ammonium ion as a prevalent and emerging nitrogen sink, when you think about it, you can transform anything that has been digested, anything, into ammonium ion. Even if you do aerobic digestion, you can, you make lots of nitrate, you can reduce that electrochemically. That's a very hot area of research. If you do anaerobic digestion, right, a lot of this thing is ammonium already. So I look at the digestion as a very available, very scalable technology that generates lots of nutrients for us to take in. So we published this in 2022 when we sort of conceptualized, where we're gonna go further. And you can use various techniques. So we explored a lot stripping distillation. So Alejandro is going to be talking about it also today. Take a look at his talk. Some colleagues in South Korea did electro concentration. So they use electrochemistry to purify ammonium ions, and everything ends up being ammonium carbonate or ammonium bicarbonate. So that's easy to do. Now, the problem is that ammonium carbonate or ammonium bicarbonate is easy to get, but it's also easy to lose. That's why in the US, it's used as, Julia, what is it used for? Fumigant, thank you. Because it's so volatile in releasing its ammonium, right? CO2 and ammonium doesn't want to stick together, right? So in my lab, what we've been working on recently is transforming, and there is a route, catalytic route, to make urea actually from ammonium carbonate, if you want to go that route. But then we, as usually, try to wrap it into our crystallization and formulation of these compounds. So if you look at our recent work, that's what we did recently. So this intriguing concept is not new, right? In China, because it's so easy to derive, it's been used for many decades until it gave way to urea. But now it reemerges again, and I have colleagues in Germany who are looking to make ammonium bicarbonate to capture CO2 with ammonia. So it all sort of converges into one thing, right? Where you end up with these nitrogen and carbon-rich compounds, and you need to think what to do with them. So no other salts needed. It's easy to precipitate. Look at again, Alejandro did that very well in his lab. Again, the challenge there is poor environmental stability, and we still need to think, how this works on a large scale, what the life cycle impacts are, and so on and so on. So we sort of were intrigued by the idea, and in Lithuania there's a huge digestion plant that generates about 30,000 tons per hour. They tell me of this thing, and so they process 800 tons a day of this tillage. And if you look at it in total nitrogen versus ammonia nitrogen, you always have about half of it, which is ammonia. It's 2, 3, 4, 5 grams a liter. So there is a energy penalty to purify that thing, unfortunately. And this presents a problem by itself because it smells. It's very unstable. If you take it to the field, it just volatilizes. So making a solid, transportable, storable fertilizer would be a very, very good thing for the industry, which is booming, which is exploding, the biogas industry. So back in 2020, with Donata's help, we worked on this already, and we did lots of conceptual modern process engineering, chemical engineering at that point in time, where we looked at how liquid digestate gets processed, through conventional distillation to ammonium carbonate. And then if you do air stripping, there is a product you can obtain. There's ammonium sulfate, but it's very difficult to compete on the market because ammonium sulfate is a byproduct of some polymer production. So I can't remember which one. So we did design process, and we sort of looked at various disposal scenarios. We went through full-blown chemical engineering, where we use sort of what's called the stripping column to strip ammonia, and what comes out at the bottom right here is a very, very clean 1 ppm ammonium that is now safe to dispose of. So we look at sort of economics, and you can see that ammonium carbonate, installed cost is just much smaller, because you have absorption, stripping, and all the moving gas compressors and so on and so on. So ammonium sulfate is much more expensive. The operating costs, since ammonium carbonate distillation needs steam or energy source, that's where most of the costs go, whereas in ammonium sulfate, that's the electricity. And then you get some operating cost recouped back when you sell these things into the market. And so to compensate somehow this cost of the reboiler steam, we came up with different scenarios. So we came up with a neat sort of scenario where you use solar energy to compensate for the steam generation. So you can imagine that during the day, this thing just circulates some hot liquid, and it distills, and then at night you can use your conventional distillation. We did extensive economic viability on that, and sort of we still found a area of operation, right, where we can get a profit right here, I suppose, in this blue shaded area, but somebody would have to pay you to take that digestate, unfortunately, right? So economics still are not very obvious in the digestate processing form. But I know there are countries that already pay people to truck these things away and dispose of them. But then what we did, and that was our, very recent and the most fun work in the lab, obviously. So with Mariana and Julia and others, we looked at making ammonium bicarbonate salts. How do we make them? We use mechanochemistry, obviously. So we sort of made these, it's not co-crystal, but it's double salts with magnesium carbonate, zinc carbonate, from bicarbonate, from ammonium carbonate. We mill them. We can do it on small scale. Now we can go into kilogram quantities. We make these double crystals where now ammonium carbonate has very different coordination. So yes, mechaноchemically, we were able to obtain these new materials: magnesium ammonium carbonate, zinc ammonium carbonate. So it's a molecular solid, right? So it's not a mixture of parent compounds. The molecular solid, it's uniform in three dimensions, right? It's the same in 3 dimensions, right? So compositionally, it's uniform. And you can look at Julia's talk today, but if you put ammonium carbonate itself, what did you grow, Julia, here? Growth inhibition. No, that was Mariana, right? So I can remember what biota she grew. So ammonium bicarbonate just kills everything, right? You can see in these experiments, nothing grows if you put ammonium bicarbonate in there. Now, if you put these salts of zinc salt and magnesium salts of ammonium bicarbonate, your biota is much happier, and it's not getting killed. So all of a sudden, you go from fumigant into a fertilizer in a sense. And the soil respiration, so instead of killing everything in soil with ammonium carbonate alone, you can see that magnesium and zinc carbonates generated much more activity in there. So to conclude, we have sort of these paradigms in nitrogen management, where we looked at improved nitrogen technologies for improved environmental impact. That's kind of redundant having two words improved there. But we're looking at developing these new products using crystal design, right? So we're trying to reinvent a little bit agricultural science and fertilizers themselves. And we are looking at completely new routes for scale up. So we're looking at mechanochemical formulations rather than solution phase chemistry. And we look at these different other products, right? So where we can use alternative nitrogen sources, so ammonium ions via circular economy. We're looking on combining nutrients into single crystals, so magnesium, sulfur, others. So our urea is much more stable without need to add these inhibitors, for example. And we just got funded with USDA and colleagues in Massachusetts and colleagues in Israel on sort of how to use these co-crystals for mulch films to make much better mulch films. So I think I'm on time. Thank you for your attention. It was sponsored by USDA 2 grants, the NSF. Israeli chemicals company is now funding it. So it's, this is a big endeavor. I try to summarize in 20 minutes. I'm done. Hold your applause. There's nothing to applaud here for. I'll let Vita go next.